Cystic fibrosis, or CF, is a genetic disorder that affects the lungs and the pancreas, where it can lead to cysts, which are fluid-filled sacs wrapped in a membrane, and fibrosis, which means excess connective tissue. CF is an autosomal recessive disorder involving the CFTR gene, which encodes for the CFTR protein. CF develops when there's a mutation in the CFTR gene, but because it's an autosomal recessive, you will need to inherit two mutated CFTR genes. CFTR protein is a channel protein that pumps chloride ions in various secretions. Since water always follows salt, these chloride ions help draw water into secretions, which ends up thinning them out. CF is responsible for a wide range of clinical manifestations, including respiratory airway disease, pancreatic failure, obstruction to small intestine, male infertility, and salty sweat. In CFTR, there are two membrane-spanning domains known as MSDs and two nucleotide-binding domains known as MBDs. The MSDs assemble to form a low-conductance chlorine-selective pore, such that its activity depends on the cycle of ATP binding and hydrolysis at the MBDs. MBD is a head-to-tail dimer with two ATP binding sites located at the dimer interface. ATP binds tightly to ATP binding site 1, which contains no ATP hydrolytic activity. By contrast, ATP is rapidly hydrolyzed from ATP to ADP in ATP binding site 2. ATP binding and hydrolysis drives the cycles of MBD dimer assembly and disassembly to induce conformational changes in the MSDs to allow anion flow. During the gating cycle, ATP binding site 1 remains tightly closed around bound ATP molecule, whereas ATP binding site 2 undergoes conformational changes, closing after binding of an ATP molecule to form the MBD dimer, but opening again after ATP cleavage to release the products of ATP hydrolysis. There are 6 general mechanisms of CFTR dysfunction. Class 3 mutations affects almost 10% of CF sufferers. Class 3 mutation disrupts the pattern of channel gating, which is detrimental towards channel function. Located in MBD1, the G551D mutation is a key residue in the LSGGQ motif of ATP binding site 2, and this mutation obstructs the conformational changes of MSDs subsequent to ATP hydrolysis. G1349D is the mirror image of G551D, located in MBD2. G1349D is a key residue in the LSHGH motif of ATP binding site 1. Mutation in G1349D influences the avidity of ATP for site 1, such that it disrupts CFTR function by hindering MBD dimerization. Current pharmacological treatments use ivacaftor, which acts on an ATP-independent pathway to favor the occupancy of the open state. With each channel opening, there is a characteristic called flicker.
Cyfloxy is the name we're given to our treatment.
Due to the pharmacological differences of G551D and G1349D mutation, we formulated 2 forms of drugs that target each mutation separately, whilst providing high potency and efficacy for the individual targets. Floxin B is a potent modulator of CFTR at low micromolar concentrations between 0.1 to 5 micromolar. Only in the presence of both pKa and NTP, Floxin B binds directly to MBD2 to slow the rate of ATP dissociation at MBD1. This in turn prolongs the duration of channel opening, thus strengthening the chlorine current in G551D mutation. IBMX is a phosphodiesterase inhibitor. At 100 micromolar, IBMX increases the avidity of ATP for site 1, favoring the correct physiological MBD dimerization in G1349D mutation.
Our drug will be delivered within a modified dynamic polyconjugate that consists of a 10 nanometer long amphiphilic polyvinyl ether backbone with shielding, targeting, and therapeutic molecules attached called Cyfloxy. With the attachment of PEG onto the polymer backbone, a hydrophilic water shield will be created, inhibiting the delivery of Cyfloxy to non-lung sites and protecting it from the immune system. The S100A12 ligand will also be attached, which can bind to the receptor for advanced glycation end products, or RAGE, which is highly expressed in type 1 alveolar epithelial cells, allowing specific delivery of Cyfloxy to the lung. Floxine B and IBMX will also be modified to add a sulfur group to their chemical structure so they can be attached to the polymer via a disulfide bond. Once a solution of Cyfloxy is administered intravenously, the dynamic polyconjugate will travel in the blood to the lung epithelium. Here, it will bind to RAGE and undergo receptor-mediated endocytosis, allowing entry into the cell. In the low pH endosome environment, the disulfide bonds attaching Floxine B and IBMX to the polymer backbone will be cleaved, allowing their release into the endosome. The negatively charged polymer will absorb protons into the endosome, increasing osmotic pressure, resulting in swelling and subsequent rupture of the endosome membrane. Thus, Floxine B and IBMX will be free in the cell cytoplasm, where they can have their therapeutic effect on CFTR.
Limitations include CAMP-dependent phosphorylation of CFTR is a prerequisite of Floxin B to augment channel activity. Floxin B only works in the presence of ATP and its action is voltage-dependent, thus it would be problematic if external chlorine ion concentrations were dramatically reduced. The exact pharmacokinetic and pharmacodynamic mechanism and properties of IBMX in prevention of ATP dissociation are yet to be fully elucidated. We believe Floxin B and IBMX is the future for treating cystic fibrosis. Investors, this is your unique chance to have a massive impact on people's lives. Floxin B and IBMX will dramatically improve the quality of life of sufferers and their families and reduce strain on the healthcare system. Join us and change the lives of cystic fibrosis sufferers and add 10% more smiles in the world.